Okay, so these are going to be the solutions. You'll find this also on the whiteboard that I will share a link to, so feel free to have a look at me solving them. So this first one, gas has a volume and a pressure, so we've got V1, we've got P1, and we've got V2. So we know that we're going to continually using P1, V1 equals P2, V2. I'm going to just quickly make this a little bit finer because of the way this is working. Right, okay, so we've got P1, V1, so we've got 20 times 3 is equal to P2 times 1.5. So we've got 20 times 3 divided by 1.5. And we get 40. So I don't know why I did that in the calculator, because that'll be, and we want to keep the units the same, Newton per meter squared. Gas increases volume, so from 10 to 50, so we've got V1, V2, initial pressure is P1, so we've got 10,000 times 10 equals, so 10,000 times 10 is equal to P2 times 50, so 10,000 times 10 over 50 is 2,000. Newtons per meter squared. Gas decreases in pressure, so we've got P1, P2. The final volume was 3. Okay, so we've got 100,000 times 1 is equal to 50,000 times 3. So 50,000 times 3 is 150,000. So we get V1 equals 1.5 centimeters cubed. Pressure changes from 100 to 20. What is the ratio for the volume change? Okay, so if we think about that, we've got, if we just do a P1, V1 equals P2, V2. So if we do P1 over P2 would equal to V1 over V2. So that's the ratio of the volume change. And we've got 100 over 20. So it equals 5. Okay. V2 over V1, sorry, my bad. Done that wrong with that. A gas occupies a volume of 500 cubic meters and a pressure of 100 kilopascals. Calculate the gas volume gas. So again, hopefully, so we've got 500 times 100 is equal to the new volume times 125. So we've got 500 times 100 divided by 125. So we get 400. No, meters cubed, no cubic meters. That's a lot. What do you need to assume about the temperature of the gas? That it is constant, or that it doesn't change. Any kind of problem like that. So that's just sort of, so something that looks a bit more like an exam question. The diagram shows a bicycle pump, which can be used for pumping air into a bicycle tire. The volume of the air is 18 centimeters cubed. Pressure is 100,000 pascals. Things placed at the pump, so we get to 6. Calculate the new air pressure. So we've got V1, P1, we've got V2. So we've got 100,000 times 18 is equal to 6 times P2. So 100,000 times 18 over 6. So 18 over 6 is 3. So we've got P2, 300,000 pascals. Two assumptions. no gas escapes or fixed mass, and no temperature change. What, if anything, has happened to the size or the diameter of the air molecules in the trapped air result? Nothing has happened to them. Okay, so the air particles are no bigger or smaller as a result. All they are doing is moving closer together. So we've reduced the space between them, but the particles themselves, they stay the same size. Explain how gas exerts a pressure on a container. Some gas is stored in a container. So key points here. So we will have things like rapid, random motion of particles. They will collide with the container. Collisions exert a force, hence there is a pressure, as P is F over A or something like that. So these are the four kind of points you get to say instead of any three of them. Something about the motion of the particles, something about collisions with the container. It doesn't matter if them colliding with each other, that doesn't. But then this idea, collisions exert a force, hence there is a pressure. So anything like that. We then have 1 gram of gas just on the container. We've got volume, excellent. So we've got Boyle's laws, we've got volumes, we've got V1, we've got P1, same mass, place a thing in there. We've got V2. So P2 is our unknown. So we've got 5 times 10 to 5 times 200 over 960. And I get that equals about 104,000 pascals. Don't want to do that. Oh, let's undo that. Put it back where it was. Right, okay. We've got a student takes a balloon to a swimming pool. The balloon is filled with an air pressure of 120 kilopascals. The volume of the balloon is 0.025 cubic meters. Takes the balloon to the bottom of the pool. The pressure inside the balloon increases by 20 kilopascals. Now this is important. Okay, this is an increase, not a new pressure. So new pressure is equal to 120 plus 20. So 140 kilopascals. So new volume. So we've got 120 times 0.025 is equal to 140 times V2. So 120 times 0.025 over 140 is 0.0214. So about 0.021. Okay, so just be a watch out for that one. It's an increase. Haha, I mean, same assumptions, same as always. Fixed mass, constant T, and I'm going to assume unicorns are awesome. That's my third assumption. Define density. So when they mean that, they just mean density is equal to mass over volume. Did the density in the air decrease, stay the same, or increase when the balloon to the bottom of the pool? Well, we've got the same mass, got a smaller volume, so our density is going to increase. And my explanation is literally what I just said. So mass of gas is unchanged, volume of balloon decreased. So that means that it will increase. Aha! Right. Now we've got this weird. Let's color one of these. There's a green balloon. Oh, artwork. That's as good as I get. A balloon seller has a cylinder of helium gas used to fill up his balloons. Volume of a balloon, 1 times 10 to the minus 2 cubic meters. Pressure in a balloon, 1.2 times 10 to the 5 newtons per meter squared. Volume of cylinder, pressure in cylinder, 1.0 times 10 to the 7. Ooh. The volume of cylinder is 0.1 meter cubed, there's helium gas. Explain in terms of particles how the helium in the cylinder produces pressure. Right, 2 marks, so it's the same thing as we had. Same stuff as we've had up here. So you know what? I'm just going to copy that. Duplicate. I hope I can then do, just paste it down here. It might not have actually taken any extra length of time. So if I right click. No. No, I've just made this. It's just the same answer. Calculate the total volume the helium gas will occupy at a pressure of 1.2 times 10 to the 5 newtons per meter squared. You can assume there's no change in temperature of helium gas. So the total volume. So what I've got to do is I've got to use the total volume. So I've got this is V1 and this is P1, and pressure 2. This is the thing I'm interested in. So I've got 1.0 times 10 to the 7 times 0.1 is equal to 1.2 times 10 to the 5 times the final volume. So that means that volume is equal to 1.7 times 0.1. And I've got 8.3 meters cubed. And then what will happen is calculate the number of balloons of that volume that the seller can fill using the gas. So if basically what this means is I've got to work out how many balloons of this I can get into this space. So what I will get is the number of balloons I can fill is equal to the total volume of gas I've got divided by the volume of one balloon. So I get 8.3 divided by 1 times 10 to the minus 2 . And we get about 833 balloons. And there we go. That's how we solve those problems.